Okay, so let's continue what we talked about last time, where we left off. So we're talking about chapter 4. And in particular, we're talking about probability. And last time we did an overview on probability. We talked about what probability was, what we were trying to find, the likelihood of an event happening in the future. And we talked about different ways in which people find probabilities in real life. And we saw that of all those ways we talked about, each of those had strict assumptions that had to be true in order to get accurate answers. And then we said that one of the ways to find probability was through mathematical approaches. And one mathematical approach we've talked about so far is the classical definition of probability. Which says that the probability of a desired event is the number of desired events divided by the number of total events. And just to put this in the context of an example, let's say that we have a jar of marbles, and each marble has a particular color and a pattern. And let's say that all the colors the marbles could possibly have are either red or blue. So that would be this horizontal axis, and then the vertical axis would be what the patterns of the marbles are, which are, let's say, either solid or striped. And each marble has a certain color and pattern. And let's say that this is the actual number of each. So let's say that we want to reach in and select a marble that is red and solid. So one approach we could find this probability is this mathematical approach, where we're finding this ratio of desired events over total events. And so in this case, what would the total number of events be? What would the number in the denominator be? Yeah, it would be 18, which is the number of individual marbles. And remember we said last time that this number you pick on the bottom is important because the number you pick on the bottom represents the total events, and you're also assuming that the number of total events here have to be equally likely. So this is a big assumption. So the total events have to be equally likely of occurring. So if you pick 18 total events here, we're implying that those 18 total events or individual marbles are each equally likely of getting selected. And we know that's true. But if we were to make a mistake and say, okay, these red and solid marbles that we're trying to select are from this group, and there's a total of 4 groups here, so why can't we say that the answer is 1 divided by 4? And what was the reply to that? Why can't we do this? Yeah.
Because each group isn't equally weighted.
Yeah, good. So this 4 representing the 4 total events here have to fit this assumption, which are the total events have to be equally likely of occurring. So these four groups of marbles are not equally likely of getting selected. Because this group here, which has 6 marbles, is twice as likely of getting selected as this group here. So these four groups are not equally likely of getting selected, and that's why we can't do this, and we can't say that there's 4 total events, because those 4 events are not equally likely to occur. But in contrast, we can do the 18 total marbles, because each individual marble is equally likely of getting selected. So of those, then what are the number of desired events representing a marble that is both red and solid?
30.
Yeah, 3 out of 18. So this would be the correct answer. And this simplifies the same fraction of 1/6. But moving forward, we'll just keep it as the unsimplified form so that you know where the numbers came from. So this answer, 3 out of 18, or equivalently 1/6, is significant. It's not just an abstract number. This is significant because it represents the same answer as if you were able to observe a number of marbles that approaches infinity. So if you're able to repeat this experiment where you have the same situation and you're selecting a random marble, and you're able to repeat this process a number of times that approaches infinity, like 1 trillion times, then in those 1 trillion times, 1/6 of the time, you're going to get the probability of this desired event of a marble that is both red and solid. So this answer is significant because it's the same answer as what you would actually observe if you were able to repeat this experiment a number of times in person. But you're able to get this answer much quicker than having to observe 1 trillion different experiments. Any questions? Okay, so moving forward then, let's say that we were trying to find the probability of a marble that is just red. So notice it's not red and solid anymore, it's just red. So we want to identify what fraction of marbles that are red. So they could be red and something else, but as long as they're red.
Well, you would add both categories that are red.
Okay, very good. So this column here that represents red, you would just count up the total of those, and that would represent everything that's red. So that would end up being 8 divided by the 18. Any questions? All right, so moving forward, we'll introduce a few more mathematical approaches to finding probabilities. So far we've talked about one, the classical definition of probability. So we'll talk about a couple more in the context of this example.
Would you not simplify the 8 and the 18?
Yeah, so normally we could and we'd get the same answer, but we're gonna leave it as this, just so you know where the numbers came from. Okay, so moving forward, so in the context of this example, this third example, let's say that we wanted to find the probability that a marble was either red or solid. So basically we want to count up all the marbles that match that description and then divide by the total number 18. So how many would match that description? So notice that these two events are separated by or, and what that means is as long as a marble is either red or solid, we want it counted. It doesn't have to be both red and solid. So how many are there that are both red or solid? That are either red or solid?
So,
Yeah, so if you look individually at each group here, these 3 match that description of being either red or solid. It just happens to be both. These 4 are either red or solid. They happen to be solid. These 5 happen to be red, so that matches. These 6 do not count because they're neither red nor solid. So there's a total of 7 plus 5, which is 12. So this ends up being 12 out of 18. Any questions? Okay, so this is one way that we found that probability by just observing the total events and then counting up each one and using this classical definition of probability. So a second way that we can do this is the next mathematical approach we'll talk about, which is something called the addition rule. So the addition rule says that if you have a probability with events structured in this way, where you have events that are joined by OR, so if you have a probability with events joined by OR, then this addition rule applies. And you can actually separate this out into individual probabilities that are joined by addition. So this would be the same thing as the probability of just event A plus the probability of just event B but now there's an extra subtraction in here, and we'll explain what that is later. But this subtraction is that you have to subtract out the probability of having an event that contains both A and B. So this is what the addition rule says, is that anytime you have a probability with events joined by OR, you can separate it out into separate events that are joined by addition, and then there's this subtraction that you apply onto it as well. But let's go ahead and apply this addition rule onto this example that we just did. So the example we just did, was the probability of red or solid. So you can think of this as a template that you're matching up here. So red would correspond to event A in the addition rule, and solid would correspond to event B. And if you're expanding this out using the addition rule, then probability of A represents the probability of what in our situation?
Red.
Yeah, probability of red, because event A is red. And then plus the probability of B, which would be what probability? Yeah, plus the probability of solid. And then minus the probability of A and B, which in this case is what?
Red and solid.
Yeah, red and solid. So now let's go ahead and fill in the numbers. So let's go ahead and substitute in the numbers for this addition rule. What's the probability of red in our example?
8.
8. Yeah, we did that in the previous example, 8 out of 18. So remember, any probability is a number between 0 and 1. 0 means it's impossible to happen, 1 means it must always happen, and then you have probabilities of anything in between. But beyond 0 and 1, probabilities aren't possible. So you can't have a probability that's negative, and you can't have a probability that's greater than 1. Alright, so in this case, the probability of red is going to be the fraction 8 divided by 18, which is the number between 0 and 1. And then what's the probability of a marble that's solid?
7.
Yeah, so solid will end up being the entire first row, so that'll be 7 divided by the total of 18. And then minus the probability of both red and solid. So it's the probability that a single event or a single marble is both red and solid. Yeah, red and solid would be 3 out of 18. So if you simplify this, you're going to get 15 minus 3 on top, which is 12 divided by 18. So this is the same answer we got before we used the addition rule. So you notice that these answers are the same. So the point is that if you have a probability with this situation where the events are joined by OR, either you can use the addition rule, or you can use the regular classical definition of probability that we had used before. And you'll get the same answer. Any questions? Okay, so now let's talk about why the addition rule works. So let's look at what we did before we used the addition rule. So the way that we got to 12 up here is we simply counted up all the events that match this description. So it would have been these 3. So these three added up together gave us that 12. But if we look at the addition rule, what's happening is we took the probability of red, which is the entire first column, and then we added the probability of solid, which ended up being the entire first row. And if you added those together, there's a number that gets added up twice. So what's that? Yeah, the number 3 gets added up twice, but you only want to add up things, just count them once. And so because of that, we have to remove out that overlap, which is what the subtraction is in the addition rule. So we have to remove out this overlap, which is occurring when you're adding up that number twice. And so that's why we're subtracting out this 3, which represents being both red and solid at the same time. Okay, so that's what that's why the addition rule works, is it's basically just making sure that you're adding up all the events once. Okay, any questions? So now that we talked about the addition rule and why it works, you might be thinking, okay, that's great that this addition rule works and we're getting the same answer we got before when we were just basically counting up all the raw events. But this addition rule looks a lot more complicated than just counting. So why do you think you would use this over, why do you think this would be useful if in this example it seems so much more complicated? Yeah.
With a larger data set, it would be a little simpler to just plug all the values into an equation.
Yeah, very good. So imagine you have a massive data set of millions or billions entries. One thing is that you don't want to have to count up all the events that match this description. You could just look at the individual probabilities and perform this one calculation. So that's one reason. Another reason is sometimes you don't even have a data set with all the raw numbers in it so that you could count things. So even if you wanted to, you wouldn't be able to count all the instances. So oftentimes you have the summaries of the probabilities, but you don't have the individual numbers like we do here. So if you have the summaries of the probabilities, then you would just use the addition rule, and you're guaranteed to get the same answer as if you had the individual numbers. So this will become really useful, and we'll see more examples of that later. Any questions so far? Okay, so that's the addition rule. Whenever you have a probability with events shown by OR, you could split the events up into separate probabilities and add and subtract. Okay, so let's look at the next example. So this will be number 4. So this is what we call a conditional probability. So let's say that you have this jar of marbles, and it's dark, and you reach in and you select the marble, and you don't know what it is, but somebody else next to you happens to be able to see it more clearly, and they tell you, oh, that marble you just selected, that's red. So knowing that the marble is red, what's the probability or likelihood now that it's solid? So, in other words, if we know that the marble's red, what's the probability that it's solid? So another way to say this, instead of saying if we know the marble is red, another way to say this is given that the marble is red. So, any ideas how to approach this question? So, if we know the marble's red, or assuming the marble's red, or given the marble's red, what's the probability it's solid now? Yeah.
You just, first you do for the denominator, you go back to like the classical thing where it's like, all possible. So you'd go to all possible reds, and there's 8 of them. So in the denominator you put 8, and then you put solid, there's only 3, so it'd be 3 over 8.
Okay, very good. So let's talk about that. So another way to say this is that given the marble's red means that out of only the red marbles. So if you look at the red marbles, how many of these total marbles are just red? Yeah, it would be this 8 representing the first column. So out of these 8 red marbles only, what fraction of those are solid? Yeah, so out of these 8, only 3 out of those 8 are solid. So the answer to this question would end up being 3 out of 8. Any questions? And so the way that we express the phrasing of this probability mathematically is this way. So this would be the notation. So we have this vertical bar in here, and the thing that is after the vertical bar is that thing that is given, or that thing that we know is true. So in this case, the marble is red would be the thing after the vertical bar, and we're trying to find the probability that it's solid. So this would be the mathematical notation, the compact way of representing this idea. And this is called a conditional probability. This is finding a probability based on some condition that is known to be true. Any questions? So this conditional probability, do you think that these two events, if we inverted them, do you think this would be the same probability?
No.
Okay, very good. So in general, it's just not true. And let's go ahead and see that in this example. So what would this probability be for this example?
37.
Okay, very good. So we're gonna look at only the solid marbles. Of those, what fraction of those are red? So only the solid marbles would be 7, and the fraction that are red is 3 out of 7. So this is an example that shows that if you have the same events around a conditional probability and you invert their order, you're going to get a result that is not necessarily the same, and oftentimes they're not equal. So these two are not equal to each other. Any questions? Okay, so this idea is really important, so I want to illustrate it with another example, more real life example, not just marbles. So let's say that we have this probability. So what this is saying is that given that it's dark, or assuming that it's already dark outside, what's the probability that it's midnight? So approximately what would that be? So ignoring like the light from the moon and assuming that we're not at like the polar caps. Yeah.
I mean, from where are we defining dark? Like 6 p.m. or
1 out of 2.
Yeah, no, dark just means that you step outside and you see that it's dark.
And you don't know our time.
Yeah, you don't know what time, so you wanna know, you wanna try to estimate what the likelihood of it being midnight at that exact point in time is. So you have no clock, you have no watch, you just step outside and you see it's dark. So what do you think the likelihood of that is? Yeah, so it's gonna be some, so we estimate that it's dark somewhere between 6 PM and 6 AM, somewhere around there, right? And so it's gonna be midnight at exactly one moment in time in that stretch. So it's gonna be one divided by a number that is much larger, one moment in time divided by many, many moments. So this is gonna be virtually zero. So that's all I want you to get for now. I don't need a more exact answer for now. But let's say that we invert these two events around the condition. So we do this. Do you expect this to be the same probability or single?
No.
So given that it's midnight outside, what's the probability that it's dark?
100%.
Yeah, 100%, very good. So this will be 1. So the point is that if you have the same two events and you invert them around a conditional probability, then they're not necessarily the same, and oftentimes they're very different probabilities. Any questions? All right, so let's talk about the fifth idea. So we've done this one before. We want to find the probability that a marble is both red and solid. And we did it before just by looking at the number of marbles that match that description. That ended up being the 3 out of 18. But it turns out that if you have a probability with this structure, where the events are joined by an and, there's a mathematical rule that addresses this, and it's called the multiplication rule. So previously we did the addition rule, and now we're going to talk about the multiplication rule. So the multiplication rule addresses probabilities with this structure, where the events are joined by and instead of or like before. So the multiplication rule says that the probability I'm going to do it for 3 events, and then we'll talk about generalizing it for any number of events. So if you have, for example, 3 events joined by and you're trying to find the probability, basically you can think of it as finding individual probabilities, where you're looking at each event in order in the list, and you're taking the probability of this first event, so the probability of A, given what came before it in the list. So in this case, what came before A in the list? Nothing. So technically, it's the probability of A given what came before it, but nothing came before it. So you can ignore that given part, because there's nothing that came before the first event. And then times the probability of the next event, which is B, given what came before it. So the probability of the next event, which is B, given what came before it, which is what?
A.
Which is A. Yeah. So given A in this case. And then times the probability of the next event, which is C, given what came before it, which is what?
B.
Which is both A and B occurring. So this is the probability of C, given A and B occurring. So this is all the multiplication rule says, is that you can separate out this complicated event into separate events joined by multiplication. And each of these will be conditional probabilities. So this will be the probability of A given what came before it, which is nothing, times the probability of the next event given what came before it, which is just event A, times the probability of the next event given what came before it, which is the previous events. This is all the multiplication rule says. So let's go ahead and expand this into the example that we just talked about. So we're going to do this probability of events joined by n. And we know that the correct answer should be 382. But let's use the multiplication rule to verify that we're getting the same answer. So the multiplication rule is saying So we're trying to find this probability that a marble is both red and solid. But in this example, we only have two events, so we can ignore this third part. So a marble being red is event A in this multiplication rule, and solid is event B in this multiplication rule. So let's go ahead and expand this out. So what's the probability of event A for our example in words? Yeah, probability of A is probability of a marble being red, so that'll be here. And then times the probability of B given A, so that'll be the probability of,
Red and solid.
okay, so B
Or
given
red
A.
or,
Yeah, so this will be solid given red. So we're just gonna substitute first, so probability of B, which is solid, given A, which is red. And then because we only have two events here, there's no event C, so we can ignore this last term. This multiplication rule extends into any number of events drawn by hand. But since we only have two events, then we only have these two terms being multiplied together. So let's go ahead and fill in the numbers here. This probability of red has what probability? In our example. Yeah, red is gonna be 8 out of 18, so that'll be up here. And then times the probability of solid given red.
3 out of 8.
Yeah, so red is 8, and of those, 3 of them are solid, so it'll be 3 out of 8. So you can punch this in your calculator to multiply them, but to get a more, an exact answer, you can also do it by hand. So you can, this is all multiplication and division between these four numbers, so you can choose to divide first. So you can divide the 8 by the 8, and then you're gonna get that 3 out of 18, which is the same as that answer we got before using the multiplication rule. So these answers you notice are the same. Any questions? So the point is that anytime you have a probability with events drawn by and, you can separate them out into individual probabilities joined by multiplication. And each of those individual probabilities end up being conditional probabilities. Any questions? Alright, so the last mathematical approach we'll talk about before we do practice is we'll talk about what it means to be a complement. So this word ends up being a homonym, which is a word that sounds the same but is spelled differently. Then another word that is complement with an I, which means that you're praising somebody. So these actually mean different things. One has an I, one has an E in it. But the complement with an E is actually also a word in real life which has a common meaning. Anybody happen to know what complement with an E means? Yeah.
That's when one thing goes with another.
Okay, very good. So if two things go together, they complement each other. But it turns out that in math, complement has even a more specific definition than that. So it's not only two things that go together, it's two things that complete each other, which means that if one person complements the other, that means that the second person is strong in something that the first person is weak at, and vice versa, so that they end up combining to form a whole person. Because individually, they're incomplete in different ways, but if they were to join together, those two complements would complete each other and form a whole person. So, in math, we have a similar idea. So, if we have all these events here, and we look at, for example, a marble being red, the complement represents all the marbles that would add to a marble being red so that you have the entire set of marbles. So if you look at all the marbles being red, you have some that are left over. So how would we describe all the marbles that are left over here? That would complete the set of all the marbles. So here we have all the marbles here. The red marbles are only 7 of them. These 10 that are remaining represent the complements of those red marbles. So how would we describe the ones that are left over?
Marbles that are blue?
Marbles that are blue, exactly. So the complement is just nothing more than describing everything that is left over from the event that is being described. So if we say that we're describing the event A as being a marble that is red, the complement of that is everything that is left over, which is the marble is blue. So that represents the complement of A. So the complement of A is that the marble is blue. And mathematically, we represent this idea of a complement in mathematical notation as the original event with a horizontal bar over it. So this represents the complement of event A, which in this case represents the marble being blue. And again, the complement is nothing more than describing all the events that are left over to form the whole. So, just like we said before, with two people who are each incomplete in different ways, but they join together to form a whole person, if we add the probability of an event plus the probability of its complement, what do you think those should add to?
1.
Yeah, it should add up to the complete event space, which is 1. So this ends up being, because if you look at this example, the probability of a red marble plus the probability of a blue marble has to add up to 1, which is the entire space of marbles. Any questions? So this is what we call the rule of complements. So the probability of an event plus the probability of its complement has to add up to 1. So this is the rule of complements. Which is the probability of an event plus the probability of its complement has to add up to 1. So oftentimes we're interested in finding the probability of a desired event, which is the probability of, let's say, event A. So if we happen to know the probability of its complement, and we're trying to find the probability of an event, then how do we use the probability of the complement to find the probability of the individual event? How do we solve for the probability of A?
1 minus the probability.
Yeah, 1 minus the probability of the complement, which is what we happen to know. So if we happen to know the probability of the complement, we just subtract from 1 to find the probability of the desired event. And so the rule of complements, you can think of either one of these two equations. They mean the same thing. One is just solving for the probability of A. And this is what we'll usually use in real life application. All right. questions? Alright, so so putting it all together, this was to illustrate some main mathematical approaches for finding probabilities. So, the very first example we did was just reviewing the classical definition of probability. That was when we just took a ratio of these two numbers, number desired over number total. So that was the first mathematical approach, classical definition of probability. And the second mathematical approach we talked about was the addition rule. This is when we have a probability of events shown by OR, then we would use this addition rule. And then the next mathematical approach we talked about was the multiplication rule. And that involves this idea of a conditional probability. So the multiplication rule says that if we have a probability with events shown by n, then we can break up those events in that probability into individual events joined by multiplication. And then the last mathematical rule we talked about was this rule of complements, which is if we happen to know how to find the complement of an event, then we know how to find the probability of that complement, then we can use that by simply subtracting from 1 to get the probability of the event we want. Okay, so this is a review of these mathematical rules. So now what we're going to do is practice using this with some more real-life examples than just marbles. Any questions so far?